Now we're looking at a sphere in three-dimensional space. And our definition of a sphere, or our sphere equation, is going to come from the three-dimensional distance formula. So here, let's look at a drawing. So we're in the first octant of R3 of three-dimensional space. Let's look or consider a ordered triple that's labeled C, and we're going to let C represent the center of the sphere. So we're going to have the ordered triple HKL representing that center point. And the definition of a sphere is that it contains the set of all ordered triples that are a fixed distance, which we'll call the radius of our sphere, away from that center point. So we're going to be going a fixed distance of R units away from that center point. And we want all the ordered triples that are this distance away from the center. So we're actually going to go all around that center point here to get all of those ordered triples. And then, but as well, we're going to go out and grab the ordered triples that are a distance of R away from that center point in all directions. So a sphere is the collection of all x, y, z ordered triples that are this distance r away from the center. And by our distance formula, we know that that distance r is going to be the square root of the one x values minus the other x value, so x minus h quantity squared plus y minus k quantity squared plus z minus the L value quantity squared. That is our distance formula, the distance between these two ordered triples. And then if we wanted to get our sphere equation, all we would really need to do is take this and square both sides. Squaring both sides gets us to our standard form of a sphere pretty quickly. So our standard form, or our graphing form for a sphere, is x minus h squared minus y, or plus y minus k squared plus z minus L's quantity squared, and that's equal to r squared. Notice how similar this standard graphing form for a sphere is to the equation of a circle in two-dimensional space. If we were to just erase this bit right here, we would have the equation of a circle in 2D. So it's nice that the equation of a sphere in 3D is so similar. If that sphere is centered at the origin, of course that center value would be 0, 0, 0. And when we have x minus 0, y minus 0, and z minus 0, that simplifies down to just being x squared plus y squared plus z squared is equal to the radius of our sphere. So that would be what a sphere centered at the origin would look like. And again, as I mentioned, our graphing form of our equation, our standard form of the equation of a sphere, is this here that does need to be memorized. So let's take a look at a quick example where we're going to find that standard form of the equation of a sphere where the center is at 2, negative 6, 4, and the radius is 5. We are going to, as a part B to this question, find the intersection of where the sphere intersects with the YZ plane, but we're going to start first of all by getting the equation of the sphere. So we know that our standard form of the equation of the sphere is x minus the x coordinate quantity squared plus y minus the y coordinate, so minus a negative 6 is plus 6 quantity squared, and then z minus the z coordinate quantity squared, and then that's going to be equal to the radius squared over here. So this is the standard form of that sphere. Let's get a little bit of a picture so we can understand this second part of the question, where or what is the intersection of this sphere with the YZ plane. So I'm actually going to pop over here to GeoGebra.com and slide down to the 3D calculator to get a visual of the question that's being asked. Let's pop our equation in here. So that was x minus 2 quantity squared plus y plus 6 quantity squared, and then plus z minus 4 quantity squared again here, and then we're equal to 25. So we have our sphere, and we can, we would be able to plot an ordered triple if we wanted to see the center, but we're actually interested in where does this sphere intersect with the YZ plane. Now, the equation of the YZ plane is simply going to be that x is equal to 0. So if we look at x is equal to 0 and run that through here, we're going to get a plane that is right on that y and z axis, right? So this is the YZ plane. Now, in order to determine what that intersection curve is between two surfaces, we've got a surface that's a sphere and a surface that's a plane. In order to determine what the intersection is between those two, we're simply going to plug one into the other. We're going to set x is equal to 0 in this equation, and we'll end up with the only two remaining variables are going to be yz, which makes sense because our intersection curve is in the yz plane. Only y and z are the ordered triples. X is going to be, are changing in those ordered triples. X will always be 0 in each one of them. So back over here, that's exactly what we need to do. We need to just plug in x is equal to 0, which is the equation of the YZ plane in our equation, and we'll end up with 0 minus 2 quantity squared plus y and z will be changing. I'll have ordered pairs that depend basically only on y and z in that plane, and the circle that results is going to be determined from this equation. So we have 4 here plus y plus 6 quantity squared plus z minus 4 quantity squared is equal to 25. And then let's subtract 4 from both sides to get that the circle equation in the YZ plane, y plus 6, z minus 4 is equal to 21. Now let's graph this equation in our GeoGebra just to check and make sure that it is actually the intersection curve between those two surfaces. So here we are back in GeoGebra, and we are going to graph the two-dimensional circle equation that we have found to be that intersection curve. Now, notice that the x coordinate is missing, and that means that what this actually is going to be is a cylinder. Because I have the x coordinate missing, it's going to extend infinitely in the direction of x. But what we're wanting to see is where that cylinder intersects with this. Is it going to pass straight through this intersection curve, which we are claiming to be this equation here, this two-dimensional equation. And so when we pop that cylinder in here, we see, yeah, it actually is. So the cylinder is going to pass through this circle 2 times, right? Because it's going to pass through in the YZ plane, and then it's going to come out of that sphere again somewhat farther out in a different constant x plane. But it does pass through the YZ plane at that intersection circle. So we are confident that this circle would have the equation, if we were looking at it in only two-dimensional space in the YZ plane without regard to any x's, this would be the equation of that circle. It's the equation of the circle in the YZ plane. So this equation, if we think of it as a two-dimensional equation in the YZ plane, it is a circle. It only turns out to be that cylinder if we're graphing this in 3 dimensions, and that would extend it in the direction of x. But in the two-dimensional YZ plane, it's just a circle.